Good morning, everyone. Good morning, friends. Welcome back to our session on neural networks. So, first of all, our sincere apologies for whatever happened in the previous day. So, in today's session, we are going to continue our journey as part of new topics. Okay. So, for that, I'm going to explain neural networks. So whatever we have learned in the previous session, we are going to recap once again, and then we'll start the new topics. So all of us, we have understood you know, the concept of neural networks. What exactly is a neural network, friends? What exactly is a neural network? Neural network, when you refer to the name neural network, it is referring to artificial neural network itself. So it is a network which is connected with neurons. Okay. And basically in a neural network, you'll have three different types of layers. Okay. So all the neurons will be connected across these three layers of neuron. Okay. So they are input layer, hidden, and output layer. So these are the three layers that we have in a neural network, and we use these, you know with the help of the neurons. We are going to pass the data, and that particular data will get trained across these three layers, and we'll get the output, right? So this is what we have discussed. Anyways, let me show it to you once again. So the basic architecture. So to the input layer, we'll pass the input data, and the data starts passing from one layer to the other layer. Okay, then finally to the output layer. But how exactly is, you know we are going to pass the input data inputs from the input layer to the output layer is with the help of two components. We use something called as weights and bias. Between each and every two neurons, wherever there is a connection, you'll have a weight component added. Okay, so within the layers of hidden layer and output layer, the neurons will have two parts. One is called activation function. Probably I should write this side. So one part will have activation function, and the other part will have summation function. Right? Yes. So what is the purpose of summation function is, when the weights get added, so these weights will be multiplied with the input values, and the weighted sum will be calculated. Simple formula is summation of Wi multiplied by xi, where I takes the value from 1 till n. So depending on number of connections that particular neuron has. So if you take neuron 2 in hidden layer, so how many connections does this particular neuron have? 2. So probably the formula will be W1 multiplied by x1 plus W2 multiplied by x2. Okay, so this particular connection will take W1 and B1 bias. In the same way, the connection between the second input neuron and the second neuron in the hidden layer will take W2, B2. So we'll talk about weights bias as well as part of coming few more topic, few more minutes. We'll discuss what are these weights and bias. So when the input values are being transformed to the hidden layer neurons, so this weighted sum gets calculated, and the weighted sum will be given as input to the activation function. So what are activation functions? Activation functions are some mathematical functions that we use So whenever you use a mathematical function, an activation function, you know, depending on the type of activation function, it will the output is going to tell whether that particular neuron has to be activated or not, right? And what we do is the output of this activation function will be multiplied with the weight, and you'll get the output over here. So this is what we do, friends, as part of forward propagation. So this entire training is called forward propagation. The data gets, the inputs will be passed from the input layer, and they'll be multiplied with the weights and get added to the bias, so that the weighted sum will be calculated, and this weighted sum will be passed to the activation function. And once after calculating the activation function, again the process continues until we get an output. Once after you get an output, you'll get loss calculated. What is the formula for loss, friends? Your actual minus predicted. What is the main purpose of neural network is to minimize this loss. The loss that we get should be minimized. So what is the meaning for that? Obviously, when will the loss will be zero? Whenever it is zero, obviously it is minimized. So when can we expect y minus y hat is zero? When y is equals to y hat. So that means your actual and predicted, if it is same, then your loss is always at the minimal condition. So this is what we are supposed to get. So in order to get the minimal loss, the model or the neural network starts back propagating. Why? Why it should back propagate? It should back propagate because the weights and the bias that is generated at each and every connection, okay, these are randomly assigned. These are randomly assigned. Since they are randomly assigned, what happens is you'll get some loss. Okay, why should we randomly assign initially? Because there is no particular rule that this much value only should be passed to weight or this value should be passed to bias. So initially they get random values, and these random values will be used for calculating the output in each and every stage, and finally loss will be calculated. Probably the loss at the initial stage will be high. In order to minimize this loss, the model, the algorithm, the neural network starts back propagating. The same, however it went forward, it starts propagating in the reverse direction, and it is called back propagation. Very important question in neural networks. Very, very important. What is back propagation? Back propagation is nothing but the model, the neural network starts propagating from the output layer to the input layer to update weights and bias. What is the main purpose of back propagating? Is to update, it helps us to update weights and bias. But how is this weights and bias updated? We have the formula here. I'll keep the formula here. See, friends. W new, nothing but new weight is given as W old minus neta into partial derivative of loss divided by partial derivative of W old. So what does this say is your new weight, since the values of weights and bias are randomly assigned, so your new weight, whatever you're going to find as part of back propagation, will be calculated using this formula. From the old weight, you are going to remove some part. And what is that part? It is nothing but eta. This is called learning rate. This is called learning rate multiplied by derivative of loss, whatever the loss that is calculated, you go and get the derivative of the loss divided by derivative of old weight. Right? So this particular value will be computed and the new weights will be assigned. I hope it's clear, right? So this is fine. New weights are calculated. That's okay. But what about bias? Even bias will be using the same formula in order to calculate new bias? Yes. For bias, the formula will be same. New bias is equals to old bias minus learning rate multiplied by derivative of loss divided by derivative of old bias. What is this learning rate? What is this loss? We have understood, right? We'll talk about learning rate also. Okay, hold on. So this is what we have discussed in the previous session, and I hope it's very clear. Okay, if someone is going to question you how a neural network is going to work, this is what you are supposed to answer. Talk about forward propagation and backward propagation, it's more than enough. But in interviews, you'll be asked questions about weights, bias, learning rate, activation functions. Okay, so these are the important topics when it comes to neural network, right? So as part of today's session, we are going to understand what are the different type, what is the purpose of activation function? Okay, then what are the different types of activation functions we have? Then what is weight? And when generally we will have weight, how are the weights get updated? We understood. And we'll also understand about bias. What is bias? And finally, loss function and cost function for different problems. Okay, we'll understand the difference between loss and cost. Making sense? Right. So I'll take up all your questions at the last, friends, but this is our agenda for the day. Right. So let us get started. All these topics were being already, covered, working and all. So I am supposed to, start from here. What is weight? Weight is a parameter. Okay, within a neural network, weight is added as a parameter. Okay, which helps us to transform input data across the layers. So you have layers, right? Input layer, hidden layer, output layer. I assume that I have took a small, network or probably one more hidden layer neuron. So if this is your neural network, input layer, hidden layer, output layer. Now, if you did not understand what is weight so far, probably you'll understand now. What exactly is weight? Weight is a parameter in a neural network. Within a neural network, weight acts as a parameter which helps us to transform the input data, okay, from the input layer till the next coming layers. So within the layers of a neural network, it helps us to transform. How? So if you have an input, this input has to be transformed to the next layer. What is the next layer? Hidden layer. So I'll have a weight added at each and every connection. Where do we have these weights generally? Each and every connection between two neurons will be associated with a weight. So this is a connection between two neurons, hidden layer, input layer. So I have a connection. Our weight will be assigned. In the same way with the second neuron of hidden layer, a new weight will be assigned. Then the same with third neuron of hidden layer. So this particular value will be multiplied with the weight, and additionally it also adds a parameter called bias. So let us talk about bias also together, because bias is also a parameter within a neural network that allows the activation function to shift left or right. So for time being, activation function, you keep it aside, but this bias helps us to shift the activation function towards right or left. Okay, so what is the role of weight? The role of weight is to determine the strength between the connections. The connection that you have between the neurons, it determines the strength. And how are they initialized randomly? You remember? initially these weights are randomly assigned. But again, if the question is like this, why? How again it is going to initialize randomly? In the backend, it uses Gaussian distribution or Savior initialization. Okay, either Gaussian distribution, Z distribution or Xavier initialization will be used to initialize weights randomly. And the values that these weights take are very small. Even bias, the values that weights and bias take will be small. Right. So initially, the inputs get multiplied. That's okay. You'll get this weighted sum, and that will be passed to the activation function, and the process continues. But when actually, they get updated as part of learning, okay, it uses optimization algorithms like gradient descent. What is gradient descent? Hold on, we'll understand. Each and every term that we are discussing, we'll understand. No worries. Probably we may not understand on the same day, but as part of this series, this playlist, we'll understand each and every topic that we discuss, right? Because all of us are new for this particular topics, neural networks, right? So we may not be good at these terminologies, what exactly they mean, how do they work, everything will be understanding as part of this playlist. No worries. So as part of back propagation within a neural network, these weights get updated. You see, they get adjusted. How are they getting adjusted? They use optimization algorithms like gradient descent. So hope you got at least an overview about gradient descent. Gradient descent is an optimization algorithm. Okay. So what kind of a optimization algorithm is what we'll discuss. Okay. So we'll talk about gradient descent in the next coming sessions, but this is the formula that it uses for adjusting weights as part of back propagation. New weight is equals to old weight minus A is representing eta, the learning rate, multiplied by partial derivative of error, nothing but loss, divided by partial derivative of old weight. Making sense? Yes. So this is how the weights get adjusted. And how are they adjusted? They use an optimization algorithm called gradient descent. We'll discuss in the next class. Probably it is not possible to discuss gradient descent in this session itself. We'll understand. Then in the same way, bias is also doing the same. Okay. They are often initialized to zero or small random values like weights. They are also initialized randomly, but in some cases they'll be initialized to zero as well because randomly assigned, right? No one knows. Like how weights are adjusted in the same way, bias also adjusts using the same optimization algorithms, right? So this is what we talk about. We understood how weights and bias work. Now let us go and understand activation functions. What is an activation function? Because actually across the neural network, in each and every neuron, apart from input layer neurons, if you take any neuron present in neural network, each and each and every neuron present in hidden layers and output layer will have activation function. Will have activation function. But what exactly is this activation function? Can you put some light on it? Yes. Friends, activation functions are nothing but some mathematical functions. They are nothing but they are some mathematical functions which are applied to each and every neuron to get output. From each and every neuron, you have to get some output, right? So in order to get that output, we need some mathematical function. That mathematical functions are nothing but activation functions. Making sense? Yes. So in hidden layer and output layer, how you are getting the output from each neuron? That is just because of activation function. And this activation function, they introduce non-linearity into the model. So into each and every layer of the neural network, they start introducing non-linearity. Why? Because the data in real world is non-linear. Okay, in majority of the cases, it is non-linear. Only in rare cases, it will be linear, friends. So in order to include the non-linearity concept into the model, even activation function helps us. And just because of introducing this non-linearity, the network starts learning the complex patterns. Isn't it? Yes. How the neural network is going to understand the pattern just because of these activation functions. Okay, so whenever if I, pass an apple, I have an image in which there is an apple. Okay, so this apple has to be understood by the neural network, right? Only if it understands the output in the output layer, we have neurons, right? The neurons that are present in the output layer will predict it is an apple. But how it is going to understand it is an apple or not? By learning the complex patterns. The pattern that is present inside this will be understood, and finally you are going to get the output as apple from the output layer neuron. And this can be done with the help of activation functions only. Okay, there are many types of activation functions. Out of all the different types of activation functions, we use majoritarily we use 6 to 7 types. That's it. If you learn these 6 to 7 types, it is more than enough. Okay, so what is these 6 to 7 types of activation functions we'll discuss. But without activation function, a neural network will be like a regression model, friends. So hope you are aware of regression model. So friends, if you haven't gone through my previous playlist, I have also done some sessions on regression and classification where we understood the important machine learning algorithms. So just go and have a look on machine learning algorithms as well, because they will be used in all these topics because they are the basics, foundations. So without these activation functions, obviously a neural network will be similar to a regression model. Because if you see regression model, what is the equation for regression model? Y is equals to beta naught plus beta 1 x1 plus beta 2 x2 plus so on plus beta n xn. Okay, where y is your output, beta naught, beta 1, beta 2, beta 3, all of them are your coefficients. x1, x2, x3, x3, so on, xn will be your inputs. So if you see here in this particular equation, the relation between inputs and output will be linear. So that is what it is trying to say. Without an activation function, the neural network, whatever we are trying to build, will be like similar to a linear regression problem. So that is why we use activation functions, and these activation functions are very important that one have to go through and understand, because they introduce non-linearity and they are responsible for the output for each and every neuron. Okay, and they also control the gradient flow. What is this gradient flow and all we'll discuss during back propagation. Whatever we are going to understand as part of gradient descent, we'll talk about this particular point there. Right. I hope you got some understanding. Right. So let us start. The types of activation functions. You see, activation functions are majorly divided into 2 types. One is linear and the other one is non-linear. Okay, one is linear and the other one is non-linear. Linear activation function, and a linear activation function we have only one. Okay, where the equation or the function is given in this way. Function f of x is equals to x. So whatever you pass the value for x will be given as output. So if you see At minus 10, if my input is minus 10, my output is also minus 10. If my input is minus 7.5, the output is also minus 7.5. So you see a straight line. What is a straight line? Is it similar to y is equals to mx? Yes. So the same straight line, that is what you see. So what happens here is, this is generally representing a linear activation function, and which cannot be used as activation function under nonlinear. It is nonlinear. And the range of this particular linear function is minus infinity to plus infinity. So depending on the input that you pass will be given as output. Okay, and this cannot get all the complex patterns that are present inside the data cannot be understood until unless if you have included some nonlinear activation functions, because they are responsible of learning the nonlinear patterns. Okay, so we use some nonlinear activation functions, and out of them, the first nonlinear function is sigmoid function. Actually, just 1 minute, Sigmoid function, I think we have already covered it as part of logistic regression, actually. Am I right? Yes, you are right. So friends, that's what I'm telling. If you haven't gone through the previous sessions of machine learning, it might be classification or regression, probably you may not grab the entire concept, but when you go through these sessions, you'll get good amount of knowledge, and that would be helping you to understand these particular topics well, right? So go through the sessions on classification and regression algorithms as well, right? So logistic regression, under logistic regression, I have explained the sigmoid function. So this is the same sigmoid function that you see here. This is the same sigmoid function. Able to see? Yes. Why it is named as sigmoid function? Because it is a S-shaped curve. Even the curve that you see is in S-shaped. What is the formula? The formula is given here. F of x is given as, the function is given as 1 by 1 plus e power minus x. So Akhil, I am able to recollect logistic regression because this is the formula that we have used. Yes, exactly. So the formula will be used since we are using exponential in the formula, we have a challenge of using sigmoid function. The challenge that we generally, or the limitation that we have is it is computationally burdened because I'm using exponential of the value, right? So obviously it will be some computationally expensive, but the main purpose of sigmoid function is it is generally used for binary classification. Even logistic regression also we have discussed the same point. Logistic regression is helping us to predict what? Probabilities. You remember? Yes. So these probabilities can lie between the range of 0 to 1. So that means any value between 0 and 1? Yes. But if the value is between 0 and 1, I can get 0 0.3, 0 0.7, 0 0.9, any value. Yes. But how it is helping us to classify a binary class task? How we are going to use sigmoid function for under binary class classification is, you see this S-shaped curve. So it is, if you exactly take the threshold as 0.5, 0.5. Okay, so the default threshold it takes is 0.5, and if the probability values, if they are less than 0.5, the value will be given as 0. The output will be given as 0. If the value is greater than 0.5, the output will be given as 1. Is it making sense now? Yes. That is how, sigmoid function helps us to work on a binary class classification task. What is binary class classification? That means in your Y column, you have only two classes, binary two, pass, fail. Okay, in order to classify pass class and fail class, okay, I can use sigmoid function where in my output layer, in the output layer, we have a neuron. Yes. So in this neuron, use activation function as sigmoid. If I keep activation function as sigmoid, so what happens? Obviously, once after calculating the probability, it checks. Is it greater than 0.5? So the output will be 1. If it is less than 0.5 or equals to 0.5, the output is 0. So this 1 is representing pass class and 0 is representing fail class. So this is how a sigmoid function helps us to, classify a binary class task. But the question comes, Akhil, that's fine. I understood whatever you have discussed earlier. It's very clear that I should use sigmoid function in the activation function as an activation function in the output layer. Fine. But can I use the same sigmoid function as an activation function in hidden layer? Is it a right approach? No, friends. It is not recommended. The reason is sigmoid function has some issues. It has some challenges, some limitations. What are the limitations that sigmoid function has? It suffers from vanishing gradient problem. It suffers from vanishing gradient problem. What is this vanishing gradient problem? If the values of x, nothing but your input, if they are high or very low, if they are very high or if they are very low, I'm talking about inputs, because once if you take input values as a very high value, it gets multiplied with weight. That is what we do, right, as part of neural network. So when it gets multiplied with weight, obviously, the weighted sum will be calculated and that should be given to activation function present in that same neuron. We are going to pass the output of weighted sum to the input of activation function. Yes. So when you pass this input to the activation function, what happens? The gradient of the sigmoid functions become very small. So you're calculating this, right? The gradient. This is called gradient. Okay. Within the back propagation, wherever the weights get updated, the bias get updated, this particular part is called gradient. And whenever you're going to get the gradient of the sigmoid function calculated, it will be close to 0. And what happens is, because of this, the learning, whatever it happens within the neural network comes down. It comes down. And moreover, it is very difficult for a neural network to update the weights. Okay, so initially you'll have weights randomly assigned. In order to get the loss minimized, what we do, we back propagate. When we back propagate, I'll use that formula. Okay, within the formula, we have the gradient. This gradient coming close to 0, what happens is the learning comes down. Okay, when the learning comes down, the updating weights is done very slow. So because of this, we cannot use sigmoid function in a hidden layer neuron. We cannot use a sigmoid function as an activation function in hidden layer neuron. And moreover, the output is not zero-centered. If you see sigmoid function, is it zero-centered? No. It is not zero-centered. It is centered around 0.5. Here, if you cut the graph exactly here, you'll get two identical parts. Is it exactly zero-centered? No. Okay, so the output of sigmoid function is always positive between 0 and 1. Yes, either 0 or 1. So this will actually cause no, the weight updates, and moreover, it leads to slower convergence. What is this convergence? We'll talk, we'll discuss. Each and every point that I'm making a note will be communicated in gradient descent algorithm, because this is the algorithm that will be used as part of backpropagation. Okay, so what is the meaning of convergence? What is slower convergence means? Everything we'll discuss, friends. Not exactly no, because when I start talking about gradient descent algorithm, probably, you'll not understand the types of activation functions. For time being, our agenda is to complete off activation functions and we'll do it. Yes. Sorry. I hope you got a clear understanding on sigmoid function. Let us move to the next function, tan h. The second one is tan h activation function. So this is again related to tan theta and all. Hope you remember trigonometry, right? So we have tan h activation function, and this tan h activation function is mathematically given with this formula. It is given with this formula. E power x minus e power minus x divided by e power x plus e power minus x, right? And the output of tan h function is always between -1 to 1. Sigmoid function, you'll get only positive values, 0 to 1. But tan h function, you can get any value between -1 to 1, right? So if you see the graph of tan h function in this image, is it similar to sigmoid function? Yes, Akhil. But what makes the difference? Akhil, I see it is not centered at 0.5. I see the centered exactly at 0. You see this line? Yes. So if I cut exactly here, will I get two identical parts? Yes. So 0 to 1 and 0 to -1. Sigmoid function is centered at 0.5, friends, but tan h function is centered at 0. So since it is centered at 0, okay, I can use this tan h function as an activation function in my hidden layer neurons. Within the hidden layer, can I use tan h function as an activation function? Yes. Why? Because it is zero centered. Since it is zero centered, it helps us to converge fast. During the training process, the converging will be very fast. So this is what convergence mean. Okay. So what is this convergence and all? I'll talk. No worries. For time being, that's okay. Even though if it is, a new topic, that's okay. So since tan h is zero centered, I can use tan h as an activation function in hidden layer neuron as an activation function. So this will help me for faster convergence during the problem. I mean, during the training. But is tan h function coming, is it overcoming the limitation of sigmoid function? Yes, only one it has overcome. What is the other one? Vanishing gradient. Still it suffers vanishing gradient. Why? Because even though if you observe for tan h activation function, the gradient will be close to 0. Since the gradient close to 0, we'll observe the vanishing gradient problem still. The weights will not be updated, as the training process goes on, the updation of weights will be very slow. Convergence is different, updating weights is different, friends. I hope you are grabbing that point. Okay, so focus. So this is again an S-shaped curve where it passes exactly to the horizon 0, 0, output and input. And if the values are greater than 0, okay, so obviously the output will be approaching 1, and if the values are less than 0, it approaches -1. So exactly at 0, you'll get the output as 0. Since it uses exponential in the formula, it is computationally expensive. So whatever activation function that we are learning, you are supposed to memorize some points. The first one is the formula. This is the important one. What is the formula for the activation function of sigmoid? f of x is given as 1 by 1 power e raised to the power 1 plus e raised to the power minus x. Then followed by, what is the output that can we get? 0, comma 1. Okay, then followed by, you should also memorize the graph. Make sure you memorize the graph, and followed by, what are the benefits that you get using sigmoid function and where it is used, in which layer is it is generally preferred to use. It is preferred in output layered neuron as an activation function for binary classification, because I'm using sigmoid function, right, which is an S-shaped curve centered at 0.5. And finally, the limitations of that particular activation function. So if you understand sigmoid function, the limitations are vanishing gradient problem, and it is not centered at 0. Now let us talk about tan h. So tan h, it is, the formula is e power x minus e power of minus x divided by e power x plus e power of minus x. Okay, so this is the tan h function formula where the output is -1 to 1. Okay, and where it is used, it can be used in hidden layers as well as output layer, but generally preferred to use in hidden layer. Why? Because the zero-centered problem that sigmoid function is facing is addressed by tan h. So that is the reason we can use it in hidden layer. But vanishing gradient problem is still there. It is not addressed. Because of the vanishing gradient problem, the gradient is exactly means the gradient is close to 0. So as the gradient becoming close to 0, the weights updating and the bias updating will be very slow. Right? So these are the points that you have to memorize. For each and every activation function, you go in the same process. Where it is preferred to use, what is the range, the function, and the problems, the limitations. Right? I'll talk about this, friends, probably in the not today's class, in the next class. Now let us go and understand the next type of activation function. It is, okay, anyhow, I'll also talk about this slide, probably the symptoms and all. So whatever you are seeing here, this is the graph of gradient descent algorithm. Okay, what is this gradient descent algorithm? We'll talk later. So the solution for the vanishing gradient problem, okay, this was given with ReLU activation function. Okay, so replacing sigmoid tan h with ReLU. ReLU stands for rectified linear unit, or we also have the variants under the ReLU. Leaky ReLU and parametric ReLU. We have ELU. We have different types of variants under ReLU function. Okay, so when you replace these sigmoid and tan h functions, instead of them, if you go with ReLU or its variants in hidden layered neurons, if we are using ReLU as an activation function in hidden layer, I'm talking about hidden layer. Okay, so you can overcome the problem of vanishing gradient. You can overcome the problem of vanishing gradient. So let us go and understand what is this ReLU, rectified linear unit. Okay, so this is what ReLU means. You see, ReLU is given with a formula. Excuse me. So the formula says f of x is equals to max of 0 comma x. Is it very simple? The formula, is it very simple? Yes. It says maximum of 0 comma x. Out of these two values, whatever the maximum value, return it as output. That's what it means. If the value of x is negative, obviously the output will be 0. Here you see this box. This is important. So this talks about the range of ReLU. If the value of x is 0, so if it is less than 0, obviously a negative value, maximum of 0 comma negative value will be 0 only, right? What if the x value is greater than 0? If it is greater than 0, again, 0 comma a value which is greater than 0. Obviously, the maximum value will be x. So I can say that the range of ReLU is 0 comma infinity. I cannot get a value which is less than 0, and I can get any value which is greater than 0 as my upper limit. So this is how you define the range for ReLU activation function. Okay, so this ReLU activation function has, you see the graph. So till here, I mean till 0, it is linear. Okay, and from here it starts. So it is a combination of both linear and non-linear function, ReLU. So what I'm trying to say is, we have an advantage of using ReLU as a function, activation function in hidden layer, because it overcomes the problem of vanishing gradient. So when you use ReLU as your activation function, what happens is exactly your vanishing gradient problem gets overcome. So what is this vanishing gradient? Understood? See, if you are going to take the ReLU as the output, obviously you'll have the values positive, if not zero. Okay, whenever you take a derivative for ReLU, you can get the positive value 1. So which means the gradient whatever the gradient value that you are discussing, derivative of loss divided by derivative of weight, old weight. So this is going to get a good value, and this is not close to 0. If it is a good number, obviously the weights that gets updated will be done in a right way. So once after holding this, once after overcoming the vanishing gradient problem, we can obviously use ReLU as an activation function in hidden layer. And moreover, it is zero-centered. So the convergence will also be fast. Even the convergence will be fast. So because of this, we can use ReLU as an activation function in hidden layer. But if someone asks what are the limitations that we have with ReLU, so what do you say? Is it computationally expensive? No, because a simple formula is being used. Because of a simple formula, I cannot even say it is also computationally expensive. No, it is not a burden for us to calculate this. This is very simple. If you understand what exactly the problem of using ReLU as an activation function in hidden layers, the challenges that we see is, you know, dying ReLU problem. Okay, so it is going to give us a dying ReLU problem. What is this dying ReLU problem? Dying ReLU problem means, what if the output of the ReLU is 0? Because the function says max of 0 comma x. So if x is negative value, what will be the output? 0. So obviously, if the output is 0, what happens? That particular, neuron becomes dead and it stops learning. So this is the major issue with ReLU and its variants. Okay, and some of the variants have overcome it anyhow, because of we have the change in the formula. Okay, so dying ReLU is the problem that we encounter in ReLU activation function, but it overcomes the vanishing gradient issue. Okay, so let us talk about the variant of ReLU. It is leaky ReLU function, which is given with the formula like this. Is it similar to ReLU? Almost similar. There is a change. The formula of ReLU is max of 0 comma x. But what is the formula for leaky ReLU? Max of 0.1 multiplied by x comma x. So you cannot get 0 here. Whatever the value of x, even if it is, until unless it is 0, if the input is 0, apart from it, if it is negative or if it is positive, you cannot get 0. and the dying ReLU problem will be fixed. And the range of leaky ReLU will be minus infinity to plus infinity, guys. Probably I should use, a square brace. Instead of square braces, I'm supposed to use normal regular braces. That would make sense because square braces means it includes, right? So minus infinity to plus infinity, anything can be given as output for leaky ReLU. And this is going to overcome the issue of ReLU. Dying ReLU will be fixed. Why? Until unless if this input is 0, only then you can get the output as 0. If not, anyhow you'll have a value. Moreover, in majority of the cases also will not get 0. The main reason is we are adding bias, right? Okay, in the weighted sum formula, if you observe, summation of I is equals to 1 till n wi multiplied by xi plus bi. This is the formula, right? So even though if the input is 0, weight multiplied by 0, again this will be 0 anyhow, this is okay. But bias will have some value. This will be given as the output. So this output will be given to activation function. Making sense? So that is the reason the dying ReLU issue will be resolved. And is it computationally expensive? No. Because we are using a small formula. This is very easy. So it maintains that computational efficiency. It is not that much issue. But if you see, it's not zero-centered, friends. Okay, this is the plot for leaky ReLU. This is ReLU and this is leaky ReLU. There is a small value multiplied to the x, that is 0.1. Okay, so because of that, there is a change, right? So we generally use leaky ReLU as part of hidden layers itself. Okay, we use ReLU and its variants as part of hidden layers only. Then we also have ELU, exponential linear unit. So when you say exponential linear unit, the formula changes. So probably here is the formula. You see, the formula is given across here. So the value will be multiplied. If it is less than 0, it calculates max of the same one, friends. Max of alpha multiplied by e power x minus 1 comma x. So between these two values, whatever the maximum value will be given as output for ELU. So like how we have leaky ReLU, in the same way we have ELU. And the output will be lying between minus alpha to infinity. Right? So this also helps us to overcome this dying ReLU problem. And the challenge that you see here is computationally it is expensive. Why? Because it uses the exponential function in the formula. Okay, because of that, we have a challenge with the exponential linear unit as well. Right? Making sense? Yes. So ReLU and its variants will be generally preferred in hidden layer neurons as activation functions. Okay, so depending on the data, depending on the size of the network, you fix the variance or the ReLU as an activation function, right? So whatever we have understood is fine, but we should also have an activation function that should be used for multi-class classification, right? So for multi-class classification, we have Softmax. So for binary class, we are using what? Sigmoid. Perfect. But for multi-class classification, if there are multiple classes that has to be classified, we use an activation function called Softmax. Softmax function will be used as an activation function in the output layer. So it uses this particular formula e power exponential, friends, e power zi divided by summation of e power again zj, where z equals to 1 till n. So multi add up all the values of the exponent divided by particular value, you know, so that you'll get the values ranging between only 0 to 1. So in short, it is also going to calculate the probabilities only. Okay. So these probabilities will be given for each and every class. Wherever there is highest probability for one class, that will be given as output. Okay. But if you see the limitations for Softmax, it is sensitive to outliers and it is more or computationally expensive. Why? Because I'm using exponent function. Since we are using exponential function in the formula, it is computationally expensive. So, and the curve is also given here, Softmax. So these are the different types of activation functions that we use as part of neural networks. And these are commonly used. I'll once again, we'll recap all the activation functions at a single glance. Coming from, we are starting from sigmoid function, which is generally preferred to use in the output layer as an activation function for binary classification. If you have two classes and if you want to classify them, go and use sigmoid function as an activation function in binary class. I mean output layer. And softmax activation function is also used in the output layer neuron only, but it is used for multi-class classification. If there are multiple classes, more than two, go and use softmax activation function in the output layer neuron. Okay, so this is also it gives the probabilities. Okay, and the values will be between 0 to 1. Wherever the value is having more value, wherever the probability is more, so obviously that value will be written as output. Okay, but if you take other activation functions, Tanh, then ReLU, its variants like ELU, leaky ReLU, all of them will be generally preferred to use in hidden layered neurons. So within hidden layers, we use activation functions like Tanh, ELU, ReLU, leaky ReLU. These are generally used. Okay, each and every type of activation function, there is a disadvantage. There are some challenges. So you are supposed to identify the challenges, understand them, as well as memorize that formula, because formula can be asked as part of interviews, and also make sure you memorize that plot, that particular graph, whatever we have for each and every activation function. You make sure you are also going to memorize it. So that is what we are going to, we have discussed in today's class. We have understood activation functions and the basics of, important terminologies like weight and bias. And in the coming session, we'll discuss loss function, cost function, and gradient descent algorithm and types. Right? So probably in the next session, we'll understand what exactly is this gradient descent. What is this optimization algorithm called gradient descent? So friends, if you have any kind of questions, yes, shoot your questions. If not, we are done for the day. And before you leave, we'll provide a feedback link. So do share your feedback. Your suggestions are accepted, and we'll try to enhance our sessions in the upcoming programs. And moreover, if you find that these sessions are, amazing, hit on the like button and do share across your connections. Ask them to join these sessions, ask them to learn these important topics as part of artificial intelligence. Okay, right. And if you have any questions, even if you are going through these sessions and if you had any questions later on, post all your questions in the comment section. Okay, I'll respond it as soon as possible. Right. So the feedback link has been provided. So complete your feedback, give your feedback, and share your thoughts. So that's all for the day. We'll meet in the next session. Until then, take care. Have a great day. Signing off. Bye.